We present the solution to problem 3, which appeared on exam 3 in fall 2014. The problem statement reads, a cylindrical pressure vessel is fabricated from steel plating that has a thickness of 20 millimeters. The material properties are given as E, 200 gigapascals, and Poisson's ratio 0.29. The radius of the pressure vessel is 225 millimeters. Determine the following. Part A, the maximum internal pressure that can be applied if the longitudinal stress is limited to 140 megapascals and the circumferential hoop stress is limited to 60 megapascals. Let's go ahead and work this problem first. Okay, maximum pressure that can be applied. We know that sigma in the longitudinal direction is equal to PR over 2T. We know that sigma hoop is equal to PR over T. We have a different stress limit for the longitudinal stress, 140 megapascals, and the hoop stress, 60 megapascals. Let's start with the longitudinal stress and solve for the pressure. The maximum pressure, we can rework this equation, is sigma longitudinal times 2T over R. We'll go ahead and substitute the stress limit for the longitudinal stress, 140 megapascals, times 2 times the thickness, given as 20 millimeters, divided by the radius, given as 225 millimeters. And the answer that we get is 24.9 megapascals. For the hoop stress, solve for P max equals sigma hoop times T over R. We'll use the stress limit for sigma hoop, which is 60 megapascals, times the thickness of 20 millimeters divided by the radius, 225. And this gives a value of 5.3 megapascals. Okay, we're finding a maximum allowable pressure in the pressure vessel. In that case, since it's a maximum allowable, the smallest value is going to control. So this value right here controls, and the answer to the problem would be P max equals 5.3 megapascals. And you clearly had to show which one of those controlled for full credit. Part B, the peak absolute maximum normal strain in the vessel, considering both in-plane and out-of-plane strains. So we're going to need to find absolute maximum normal strain. Clearly show which one controls. It's implicit in the problem that we want to use the controlling pressure from part A to solve for the maximum strain in part B. The longitudinal strain, epsilon x, or epsilon longitudinal, is PR over ET times 1/2 minus nu. The hoop strain, or epsilon y, is PR over ET times 1 minus nu over 2. And the out-of-plane strain, epsilon z, is PR over ET times -3/2 nu. They all have the same factor on front, so I'm going to consider these terms to determine which one controls. 1/2 minus nu is equal to 0.21. 1 minus nu over 2 is equal to 0.855. 3/2 Poisson's ratio is equal to 0.435. So the largest value is clearly this one, and this epsilon y is going to be the controlling value here. So I'll solve for epsilon y. Epsilon y, or epsilon hoop, PR over ET times 1 minus nu over 2, substituting my values, the maximum P in part A, allowable P, the radius 225 millimeters, the elastic modulus 200 gigapascals, or 200 times 10 to the 3rd megapascals, and my thickness of 20 millimeters, the value of 1 minus nu over 2, which I computed as 0.855. That reduces to 2.56 times 10 to the -4th. All the units should cancel out. You can leave the answer as in that form or express it as 256 microstrains. Either of those would be acceptable. That concludes this problem.